Okay, so we're back on slide 23 here. Some hints for calorimetry problems. You have to list your givens, and it's best to probably do it in two columns so that you're keeping the metal separate from the water givens. It takes about a half a page to do a calorimetry problem, so allow yourself plenty of space and don't worry about trying to use as little paper as possible. It's good if you leave gaps here and there. Now your delta T is always going to be negative if your material, your substance is cooling down. And you're going to have a positive delta T if the material is warming up. So keep that negative where the negative goes. Okay, it's pretty easy to check your work. The heat of the metal should be pretty darn close, but opposite in value to the heat of your water. So plug the values in and see if it works. The final temperature will always be the same for the metal and the water. Always, always, always. They are in the calorimeter together, and so when they reach equilibrium, the temperatures have to be the same for both. All right, so keep those things in mind. Now, here's a second example of a calorimetry problem, and I do want you to solve this with me on your paper. At the end of these slides, if you would pause the podcast and fill in what I ask you to fill in, that'll be wonderful. So if you don't have a calculator yet, you better get one. Pencil, get one. Paper, nice, fresh and clean paper. Add it to your notes, whatever. Just make sure you have plenty of space to write, okay? So you're going to have a couple of columns here. Label one at the top metal, the other one water. Read through the problem carefully. We have Callie who heated a bar of aluminum and then she dropped it in a calorimeter that contained 100 grams of water at 23 Celsius. The temperature of the water and the bar of aluminum then rose to 32 degrees Celsius and dropped, of course, to 32 degrees Celsius. At what initial temperature must the aluminum have been? Now go ahead and fill in your data here. Make sure that you're writing the correct units. Make sure you're keeping the metal straight and the water straight. Now, in terms of the delta T, it's asking you to solve for initial temperature. As with the specific heat problems, though, remember you're going to have to solve for delta T of the metal first, so keep that in mind. If you want to pause here and make your list, that's great. So hopefully you've made your list. It should look much like this list right here. Include as much information as you can. And please put the little subscript M for the metal and W for the water. Keep every single unit with the measurement. Okay, so after you have these listed, just go ahead and check to make sure you have the right things listed. You're going to state your basic equation. So just like with density problems or specific heat problems, you always state your basic equation. Now remember, you have to put this negative sign in here to show that the metal is what is losing heat energy. Okay, no negative here with the water. Okay, so in this particular case, we're solving for delta T of the metal, knowing that then our next step after we get delta T of the metal is to solve for the initial temperature of the metal. Okay, so what we need to do here is rearrange. We're going to solve for delta T. And if you compare the rearranged equation to what's on the left, all you see is that C delta T of the metal has to be divided into both of these sides. So divide both sides by C delta T of the metal and you do end up with this. Negative sign is still intact. Write down the basic and the rearranged equation now and pause for a moment if we need to. So at the top of the page here again, this is your rearranged equation. And this is what you should have plugged in. Please double check to make sure you have units with your substances. And also make sure that you're carrying all these zeros here with you. If you don't carry these zeros, your significant figures get very, very messed up. So make sure you're always carrying all your significant figures. Okay, so in this particular problem here with your plug-in, remember your delta T of the metal, you have to make sure that you cancel your units. So grams and grams cancel, and we have two specific heats, so all of those units cancel, and we're left with degrees Celsius. Now, if you take a look here, unlike the last problem where we had a negative temperature change, a negative delta T, we have a positive delta T. So this negative then is going to be carried through down to here. So you're going to multiply, 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 divide, and also divide. And your unit's going to be degrees Celsius, keeping the negative in there. 5, 4, 3, 4, and 3 significant figures. So we'll just go with 3 here. Okay, so keep in mind that this delta T is equal to the final temperature of the metal minus the initial temperature of the metal. Yes, we are solving for the initial temperature of the metal, so we're going to have to rearrange this a little bit. So let's fill in the gaps here. Here's our delta T of the metal. Here's our final temperature of the metal minus Ti. So at this point, we're going to use algebra. So let me just stop here and let you know what it is that we expect of you. What you're going to see below is exactly what we did algebraically to solve this problem. At this point, if you simply want to rearrange this top equation and make sure everything's plugged in and solve for your answer, that's great. You're only going to get points up to here, though, if anything goes wrong. If anything goes wrong from here to the end, you will not be given partial credit. If, on the other hand, you choose to go ahead and do what we've done here and show all your work, you will be awarded partial credit depending upon what you've done correctly. So algebraically, here's what we have. And you don't just say, okay, here's the delta T and throw it on the page for us. You do have to rearrange this equation and solve to get points, but you can also do it this way. What you do first of all is you see that you have plus a negative Ti on this side. So what we would do then is we would add Ti to both sides in order for this to cancel. Okay, you've done this algebraically. Okay, so then at this point what we're looking at is we have a negative 50.6 degrees Celsius on this side. So what we're going to do is get rid of this so that we're going to leave our Ti all alone. So you're going to add 50.6 to both sides, 50.6 here, and then you're also going to add 50.6 over here. When you add 32 then to 50.6, you get 82.6, and your delta T was negative 50.6, which means that your initial temperature was 82.6. Now, stop and think. Stop and think. This is your initial temperature. Now, what is this the initial temperature of? It's the initial temperature of the metal. Okay, it's the initial temperature of the metal. Now, does this make sense? If you have an initial temperature of 82.6 and you have a final temperature, where's my final temperature? Oh, it's on the last page. Your final temperature is going to be, oh, here we go, 32.00 degrees Celsius. Does 32 minus 82.6 make sense? Ti, Tf. So it's going to be Tf minus Ti, and of course we'll have a negative number, and yes, it does make sense. This negative here means that heat energy is lost, and so therefore our temperature is going to go down. So just stop for a minute and think about it. Okay? Now, what's going to happen next is you are going to be working on problems in the last page of your packet. And for tomorrow, your homework is posted on the wiki, but if you go to pages 26 and 27, you're going to see 2 problems on the front and 3 problems on the back. Now I want to point out something to you. If you go to page 26, the front side, what you are going to see is a different way of solving these calorimetry problems. Now let me make this real clear. This is not the way that we want you to solve these problems. This is a way to help you make sense of what is going on with the calorimeter, in the water, with the ingot, and so forth. And this is also a method that helps some people to kind of prioritize and to understand what's going on a little bit better. So if you follow the instructions on 26, there's 2 problems. All you have to do is to make sure that in each of these calculations you have a list for whatever you need and that you go ahead and you solve accurately, and you're going to go from one letter to the next letter using the previous answer. So those are pretty much straightforward. You should get the same answers as if you just use MC delta T of the metal times MC delta T of the water. So just make sure that you understand that this is not how we want you to show your work, but it's a logical method to help people to understand a little bit better what's going on with the calorimetry experiments. So if you go to the back, page 3, 4, and 5, you have 3 remaining calorimetry problems. If you want to do these on a separate piece of paper because you're going to have more space, no problem, go ahead and do it. Make sure that all of your work is clearly labeled and make sure it's all very neat and very clear. We will not be giving any credit for people who do not show work in the exact way that we've indicated in class. End of story. Doesn't matter what your answer is. Doesn't matter how much chicken scratch you have on your paper. If you're not doing it the way that we're telling you to do it, then we're not giving you any credit. You're not going to get a stamp, and you're not going to get any credit, and there are no late papers. Okay? So I hope you enjoy your lab tomorrow. Pay attention to what your homework is on the wiki and read the agenda very, very clearly. Come to the lab room tomorrow with the appropriate lab wear. Okay? Shoes, old clothes, no baggy sleeves. Okay? Talk to you later. Adios.